All right, so for those of you who were here on Monday for the makeup lecture, I'm going to back up just a skosh to hydrogen bonds. And so those of you who weren't here, hopefully you've read a little bit about electrons and read about bonds, and I will re-record that lecture for you, but I'm going to move forward for those of us who already heard that and talk about our sort of third category of bonds. So we talked about ionic bonds being electrical attractions between two ions. We talked about covalent bonds being when atoms share pairs of electrons, right? And then there's van der Waal interactions. And van der Waal interactions are kind of different because they're not really about losing or gaining electrons or sharing electrons. Instead, they're attractions between molecules or parts of molecules. These attractions usually have to do with partial charges. So they're caused by polarity in molecules that are formed by polar covalent bonds. And then those polarities allow attractions and interactions to occur. Okay, so the picture I have up here is a picture of gecko toes. Because this is just one of those really cool examples. Geckos are able to climb perfectly flat surfaces, surfaces that have almost no texture to them at all, because they have small little electrical charges in the pads of their toes. And they can use that little bit of partial charge to adhere to the partial charge of the surface, and then they can climb straight up a wall. And so if you've ever watched a gecko climb, they're very fast and efficient, and they're never worried about falling off. But they're being held onto that wall, not by any kind of suction, but by little small partial charges in the pads of their toes. And that's a van der Waal interaction. A specific type of van der Waal interaction is the hydrogen bond. And hydrogen bonds are going to be really important in our discussion today about water in our lab next week when we talk about the properties of water. And so hydrogen bonds are attractions between the partial negative charge. So that parentheses around this negative here tells us this is a partial charge. It's not an ion, it's just a partial charge, okay, due to polarity. The partial negative end of one molecule, and that's usually something really electronegative like oxygen or nitrogen, and the partial positive charge of a hydrogen atom. So it's called a hydrogen bond because this partial positive charge of the hydrogen atom is important. So if we look just at a water molecule, let's just look at this water molecule in the center and pretend that the rest of them aren't there, okay, for now. If we look at this water molecule, we have our oxygen molecule in the center, and we have our two hydrogens over here, and we have a covalent bond between that hydrogen and that oxygen, and we have another covalent bond here, right? Those single black lines are strong, they're not dotted. They show us a strong bond. That bond is a covalent bond. And because of oxygen's electron greediness, right, the fact that it wants to hold those electrons close to it, this oxygen becomes partially positively charged, and the hydrogens becomes partially negatively charged. The hydrogens become partially positively charged, and this is a polar covalent bond. Okay, so this bond right here, and this bond right here are polar covalent bonds. Those polar covalent bonds result in these partial negative charges on the oxygen, and the oxygen has two areas of partial negative charge where it is associating with the hydrogen and where it's stealing or being greedy about that hydrogen's electrons, okay? And then the hydrogens each have these partial positive charges, one per hydrogen, and that's the region of the hydrogen that isn't getting enough time with that electron because it's spending too much time with the oxygen, okay? That creates this individual water molecule. Because of these partial charges, this water molecule can be attracted to other things that have partial charges, like another water molecule. So this bond here between this partial positive of this water molecule and the partial negative of this water molecule is a hydrogen bond. And it's dotted in our diagrams to show that it's a relatively weak bond. Okay? It's easily broken. It's broken by mild force or pressure. It's broken by molecular disturbance, the movement of molecules. It's a fairly weak bond by itself. Now, if you have a bunch of molecules all bonded together by hydrogen bonds, it can be a relatively strong bond, like in mass. But individually, each hydrogen bond is pretty weak and easy to disturb or break. Okay? Any given water molecule is going to be able to bind to up to 4 other water molecules, because there's a partial positive charge on this hydrogen, and it can bond with one. There are 2 partial negative charges. Each of those can bond with a water molecule. And then there's this partial positive charge here that can bond to that one. So each individual water molecule can bond to 4 other molecules via hydrogen bonding. You guys have any questions about that? I reviewed covalent bonding there a little bit too, for those of you who weren't here on Monday.
So you can have covalent.
Yeah, so the covalent bond is what's holding all of these individual water molecules together. So this bond here, polar covalent bond, and then you can't see it, but there's polar covalent bond there, polar covalent bond there, there, there. And the dotted is the hydrogen bond, which is a type of van der Waal interaction. Yep. And so those solid lines, strong bond, firm. Dotted lines, relatively weak bond, easy to break. Okay, so you get a lot of information from these diagrams if you look at them carefully. Okay, it's important to know that hydrogen bonds don't only occur between water molecules. That's like the classic example. We're going to look at that in lab next week. It's easy to think about. We're going to talk about it as we talk about water. But hydrogen bonds occur anytime you have a partially positive hydrogen and partially negative atom somewhere else in the molecule or in another molecule. Hydrogen bonds are essential in building our large molecules. So we're going to spend all of chapter 3 talking about our large molecules, and hydrogen bonds are essential in all of those. Okay? Hydrogen bonding is essential in shaping things. It gives our molecules 3-dimensional shape. It's essential in holding our DNA together. Okay? So these bonds are really important, and they occur in places other than in water. In this chapter, we're going to mostly focus on water. But here, we can look and see this is a large molecule. We'll say that that's a protein. It looks like a protein to me. And we're not seeing all of the thousands and maybe even millions of atoms that are making up that large blob of the molecule. But out here on the end, we have a nitrogen that is bound to a hydrogen, and this hydrogen has a partial positive charge. And over here, we have an oxygen that has a partial negative charge. And those two form a hydrogen bond, and in doing so, shape that molecule. Okay? This molecule might otherwise be linear, but because of the attraction between those two ends, it folds and grabs and holds tight here. Okay? If I break this bond, right, then this whole molecule opens up. And it's no longer going to have a C shape, but it's just like a glob, right? It loses its important structure. So that hydrogen bond is essential to the shape of that molecule. And this is just showing you the actual atoms. So in biological systems, covalent bonds are the strongest bonds. Okay? And that's because they are strong in water. Our ionic bonds, which in a chemistry class would be the strongest bond, are weakened by the aqueous system of biological environments. Okay? And although you don't think about yourself as being a water-based organism, probably, your body is 70% water by volume. So all of the reactions that are happening in your body are happening in water. So the bonds that are in your body are in water, and therefore ionic bonds are in the middle. They're not as strong as covalent bonds. Okay. Then the van der Waals interactions, which include hydrogen bonds, those are our weakest. Again, in force, with lots of them together, they can be important and powerful, but a single individual hydrogen bond is relatively easy to break. Okay. You guys have any questions about that? So for those of you that are unsure about some of what we just talked about with bonds, I will record that lecture and get it posted, re-record that lecture so you have that background information on electrons and bonding. What I want to do is move forward and talk about water. Okay. I just said much of your body is water, right? Water is really important for biological life. When we started off this chapter, we talked about the states of matter, right? If you look in this picture, you can see water in all three physical states, all in one place, right? Where do we see liquid water in this picture? In the lake, right? Out here. This is our liquid. Where do we see solid water? Our ice. Where's the gaseous water? Up in the clouds, right? So we have gaseous water as water vapor in the clouds. We have liquid water in our lake or inlet, and then we have our ice here, and here, and here, which is our solid water. Okay, water exists in all three states simultaneously. It interconverts between these states regularly, and that interconversion is temperature dependent. Okay. Listen, in this natural environment, obviously water is very important, right? When we think about going out anywhere in the world, we are experiencing water vapor in our atmosphere. There's water vapor in our atmosphere right now. We would feel it a lot if it were July, right, when the humidity goes up. Life also evolved in water. The oceans that are on our planet now are actually quite small relative to some of the original oceans on our planet, and the amount of water on the planet has increased and decreased at different times in terms of liquid water. But all of the evolution of life happened in water, and much of life occurred in water for a fairly long period of time before any of it came to the terrestrial land environment. Okay? Because of that, most of life is just really highly dependent on water. Our individual cells for a plant can be as much as 90% water. And so this plant cell over here, if you look, there's this big structure in the center called the central vacuole, and that is just a giant reservoir full of water. Okay? Human red blood cells are about 51% water. A regular cell in the human body is anywhere between 65 and 90% water, and the body itself is 70% by volume water. So all of the things that are happening in any of these systems, in a plant's body and an animal's body, are happening in a water-based environment. We have to regulate our water loss to the atmosphere around us. We have to make sure we retain our water. We have to drink and supplement water that we lose evaporatively. And all of our reactions are occurring in water. Okay. We just talked about the fact that water is a polar molecule, right? And that water forms hydrogen bonds with each other, and water can form hydrogen bonds with other substances. Okay. So that's nothing new, but it's important to remember, like, that is the foundation of all of these special features that we're going to talk about relating to water. The reason water has cohesion and adhesion and causes surface tension and all the things that we're going to talk about come from ultimately water's polarity. Okay? And the fact that it can hydrogen bond with other water molecules. Okay. All right, so let's start by thinking about that polarity and what that means for how water interacts with other things. Okay. When water molecules come in contact with other molecules, those molecules might want to interact with water, or they might not want to interact with water. Those things that want to interact with water are known as hydrophilic. And from a root term, hydro means water. Philic means loving or affection for, allegiance to. So a hydrophilic molecule is a molecule that wants to interact with water. It's typically a polar molecule, and it is readily going to interact with water. So if I drop something like carbon monoxide or NH3 into water, it's just going to evenly disperse and blend in with that water and interact with it freely. Hydrophobic molecules, hydro again meaning water and phobic meaning fearing, not really fearing, but they don't want to interact with water. They're going to turn away from the water and they're going to try to come towards each other. So things that are hydrophobic tend to be nonpolar and they interact with each other, but they avoid water. So if you think of something like hydrocarbons, like a fuel, you could be thinking of like a gasoline or benzene or propane, all of those things are hydrocarbons. You could think of a droplet of oil, right? Something that when it goes into water is going to cluster with itself, but it's going to avoid the water. Okay, so here, these little methane bubbles, each one of those little methane molecules is coming to the other methane molecules, and it is avoiding all of the surrounding water molecules. So you make a little pocket of methane, and the water stays to the outside, and those hydrocarbons or those hydrophobic molecules come together. Okay. So we can think of this if you imagine dropping some food coloring into a container of water, it's just going to spread out, right? And you could watch it. It would look like this at the beginning, and you watch it for a few minutes, and it's going to spread out some more. And 5 minutes later, the whole container is all going to be pale blue, and the food coloring will be evenly distributed, right? And that's because those dye molecules are hydrophilic. They interact well with the water, they distribute amongst the water molecules, and they fill up that space, and the whole fluid becomes dyed with blue, right? If I drop some oil into a glass of water, I can stir it, I can shake it, I can stir it some more, right? I can break up those oil droplets into little tiny pieces, and as soon as I take my stirring or agitation away, the oil molecules are going to come back together and clump back up, and they'll eventually form a film, right, that is completely separate from the water. All the oil molecules will come together and separate themselves from the water, and that's because they're hydrophobic. Okay. Does that make sense? Okay. So when we think about water, we're going to talk about water having some special properties. And the first of those are adhesion and cohesion, direct result of water's hydrogen bonding. Okay. High heat capacity and high heat evaporization. We're going to talk about what that means. Water is a universal solvent, which means that it readily dissolves polar molecules like that food dye from the previous example. And then water also disassociates into its component ions and reassociates. And because of that, there is a pH value associated with water-based solutions, and we'll talk about the pH scale. Okay, so as we go through water, we're going to talk about each of these things. It's the wrong Olympics, but if it were Summer Olympics instead of Winter Olympics, if you see this swimmer, if you look carefully in this picture, I'll switch colors here, you can see the water is actually coming up over and forming a film around the swimmer's head and a film over his mouth, right? That is all due to surface tension. Those water molecules are actually hydrogen bonding together and creating a film over the swimmer's body. We'll look at how that happens. You guys have this slide? Still writing? I know, it's a little wordy. This is why I try not to put words on my slides. All right. So if you can envision that picture that we just looked at of hydrogen bonding, where one water molecule is connected to all of the surrounding water molecules, right? Each one of those hydrogen bonds is relatively weak, but together, it's fairly strong force. And all of those water molecules can be attracted to all of the neighboring water molecules around it. Okay? Because of that hydrogen bonding, water molecules resist coming apart. If you think about our states of matter where we had liquid and molecules are just moving around in their volume of space, or in air, they're moving around their volume of space. If you add in hydrogen bonds, all of a sudden those water molecules in that liquid are not moving as freely because they're resisting coming apart and they're staying closer to each other. Okay? That is called cohesion. I don't know what else to do about it. So cohesion just means the molecules of the same kind stick together. So when we use the term cohesion, we're talking about things that are the same sticking together. Okay. So water molecules cohere, and they form droplets, bubbles, or surface tension, right? I forgot to ask you guys if everybody's okay with seeing pictures of spiders. Hopefully, like, this is the cutest spider, right? Not only is it an adorable jumping spider, which is my favorite kind of spider, it's wearing a hat, right? Like, doesn't that just make it so much cuter? So the thing that is making this droplet stick together is cohesion, right? All of the molecules that are part of that little bit of water are holding to each other. And because they're holding to each other, they're just forming a little droplet hat. They're not running down over the spider's face, right? The same thing is true on this dragonfly. All of those little beads of water are dewdrops that have collected together, and the waters are cohering, the water molecules are cohering to each other. And so they're not running like a free-flowing liquid because hydrogen bonds are holding them together in droplets. Okay. Does that make sense? All right. That cohesion that holds those water molecules together also creates surface tension, right? So if you've ever been at some still water, whether that's a pond or a river or a lake where the water is still, and you see little insects running around on the surface of the water, right? This is a water strider over here. And you can see at each point where his leg comes into contact with the water, there's like a little dimple or a divot on the water. And it's almost as if the water is a solid, right? What's causing that surface are all of those water molecules at the surface of that calm water being hydrogen bound together. And this little guy has so little mass, his body is so lightweight, that he can stay on top of that water tension. He doesn't break through. So the hydrogen bonds are strong enough to hold together even with the pressure of the water strider's body on them, right? If I stuck my finger into that very same water, or I tried to step onto it, we're all done, right? All of the hydrogen bonds would be broken, and I would bust right through that surface tension. But the spider can or the water strider can walk on water. This jaguar, as it surfaces and comes up from the underneath and comes up under that surface tension where all of those water molecules are solid at the surface, it's actually pushing that layer. And that's where you get that bubble, just like you did on the swimmer, that bubble over it, because it's pulling on that surface tension. And then at some point, his head's going to come far enough above the water, the surface tension is going to break, and the bubble is going to burst, and the water is going to run away, right? Okay. Does anybody here play Ultimate Frisbee? A couple of you. Do you know why you should never accept the challenge to drink the contents of a Frisbee? Surface tension. You can fit 4 beers in a standard Frisbee. Do it. You make a big bubble on the top. Surface tension just keeps filling, right? It's the reason you can overflow a glass. It's the reason if you have a straw in your drink that the water in the straw is higher than in the glass itself. It's that property of hydrogen bonding of water. Water is also adhesive. What? Oh, great. Of course, you'd be the one I inspire. Water is also adhesive. So you think about an adhesive, something that you call an adhesive, might be tape or glue, right? It sticks something to something that's not itself. So adhesion is clinging of one substance to another. So cohesion is water sticking to itself, and adhesion is water sticking to something else, or something else sticking to something else, right? Gum adheres to the underside of a table. Hopefully not. People still do it. Or water molecules can adhere to another substance. So here in this picture, we have these individual evergreen needles, right? And again, dewdrops hanging from the underside of those needles, right? The droplet itself is cohesion. The water molecules are sticking to each other. And then the droplet adhering to the needle, that's adhesion. It's hanging from that. And again, just like surface tension, there's a limit, right? As dew continues to condense on the surface, if that water droplet gets bigger and bigger, eventually it's going to have too much water collected together and it's going to fall to gravity, right? The force of gravity will be stronger than the force of adhesion. But a small droplet, like this guy, those can just keep hanging. Okay? So adhesion is clinging of one surface to another. You have another picture there? No. So when you think about a straw in a glass, again, I should have brought a straw, no, but usually somebody has one, and there's fluid inside the straw, and the fluid in the straw is higher than it is in the glass. That's because it's climbing up the sides of the straw, right? When we worked in lab last time and we looked at measuring things in a graduated cylinder, and I said that we wanted that little meniscus to sit on the line, right? And as you looked in your graduated cylinder, there was a curve. That's because over here, the water is adhering to the glass. It's just climbing the surface of the glass. And that's because of the hydrogen bonding properties of water, and because glass is a silicate and it has a little bit of charge to it, and it climbs up there. Okay. All right. So let's return back to our three states of matter. Here we have all three states again. We have liquid water down here in the ocean. We've got our solid ice in the glacier, and then gaseous water vapor up in the clouds. Okay. When I described the states of matter, I was talking about how much movement there is between the molecules, right? In a solid, the water molecules are moving very little. They're just kind of vibrating in place. So in solid water, all of the water molecules are hydrogen bound to the maximum possible other water molecules. So remember, each water molecule could hydrogen bond to 4 others, right? And the bond length of those hydrogen bonds is specific, and that's what forms the crystal structure of ice. Okay? So each one of these water molecules is going to be bound to its requisite number of other water molecules, 4 others. They're not all drawn here. And the length of those hydrogen bonds is consistent between water molecules. So all of those individual water molecules are equidistant to each other. Okay? They're not packed completely together the way most solids are, right? Many solids, the atoms line up, or the molecules line up right adjacent to each other. But in water, because of hydrogen bonding, the water forms hydrogen bonds first, and then the molecules keep slowing down, and they stay at their hydrogen bond distance. And so there's actually a solid water is a lattice. There's an open structure there. Okay. In liquid water, some of the water molecules are hydrogen bound to each other, but not all of them. Some water molecules are free floating. They tend to form more hydrogen bonds as the temperature of the water cools and they get closer towards solidifying. And they tend to form more hydrogen bonds when there isn't a lot of action in the water. So either the molecules are moving faster because of temperature, or the molecules are moving faster because of wave action, because of wind at the surface, right? So if you've got a lot of wind blowing across the surface of water, then the hydrogen bonding is going to be disrupted all the time. But on calm water, you'll form that surface tension at the surface where the hydrogen bonds pull the water molecules together. But because liquid water is not frozen, it's not solid, some of those molecules are always going to be moving. So those hydrogen bonds are formed and then broken and reformed and broken. And this water molecule breaks off of this one and comes over to this one. And they move around in space, forming temporary hydrogen bonds, breaking apart and forming another hydrogen bond. So they're always in motion. Okay. In gaseous water, there are no hydrogen bonds because the water molecules are too far apart and moving too much, and they don't come together and form those bonds. Okay. Does this make sense? Mm-hmm. 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 Yeah. So usually watercolor is actually independent of the water molecules themselves, but is an effect of the other things that are in the water and the reflective and absorptive properties of those, and also water depth and surrounding vegetation. And so the color really has to do with how the light is hitting the water when you look at the body of the water. Now, if you take a scoop of it and put it in a glass and a scoop of the other water and put it in a glass and they are different colors, then that's usually because of something that's in the water, either algae or some kind of life, some invertebrate life that you can't see, or the byproducts of that life, or sediment. And so if you have a lot of erosion, you end up with water that gets kind of darker and cloudier, and that's because particles are floating in the water and discoloring it. It's not really due to the water molecules themselves or to the hydrogen bonding, but actually to what's in the water that's something other than water molecules, or how that water is receiving and reflecting sunlight. Okay, it's something actually in the water. Yeah, I don't know. We should look up the name of the lake and we'll figure out some more information. Okay. So I mentioned that solid ice or that solid water, right, when it freezes to form ice, is going to have each little water molecule at one hydrogen bond's length from all of its surrounding neighbors, right? And that creates that open structure. So as we see up here, we have this sort of open structure where there's space between. Because of that, solid ice is actually less dense than water. So most things, if you have the solid of a substance and the liquid of a substance and you put them together, the solid's going to sink because solid is heavy. But in water, the solid actually floats, right? Anybody who's ever had ice in a glass of a drink, the ice is floating on the surface, right? And that's because this space that's created by hydrogen bonding makes that liquid more dense than the solid, and the solid comes to the surface. Over here, if I had some frozen benzene and I dropped it into some liquid benzene, it would just sink. And that's because it's solid and it's denser and it's going to sink down because its individual components, its individual atoms are going to be packed more tightly together. They don't have that open space. Okay. Can you think of what impact this might have for life? Imagine you're a fish that lives in a pond in New England. Right. So if liquid ice were denser, I'm sorry, if solid ice were denser than liquid water, a pond would freeze from the bottom up, right? Or the river would freeze from the bottom up, and everything below it would freeze solid. As it is, the pond and the lake and the river freeze from the top down because that ice is less dense, right? And so life can remain under the water. And like you said, that becomes an insulating layer. right? The ice itself then starts to buffer the water below from the cold ambient temperature above, and it further prevents additional freezing below. Okay? That's really, really important for lots of forms of life, right? Turtles, fish, some frogs, they can spend the entire winter in the water below the ice, and they just get their oxygen needs met from getting the oxygen out of the water. Sometimes when there's cracks in the ice, some of them will surface. Actually, somebody just sent me a video of a snapping turtle surfacing through cracks in the ice the other day. It was swimming, coming up to the surface. So that protects lakes and oceans from freezing from the bottom up, right? And because those hydrogen bonds are stable in ice and temporary in liquid, the liquid below can still form some hydrogen bonds at the surface and then break and form more and break. And if the temperature drops, they may form more bonds and become part of the solid on the underside of that ice. But any freezing is going to happen from the top down. Okay. So now I have some words that are underlined here, which means I'm not going to ask you to define these, but we need to understand these concepts in order to think about the next special property of water. Okay, so I want to first define temperature, and I feel like we already had this conversation in this class. We had this conversation the other day about what temperature is. Yeah. So temperature is just the speed at which a molecule is moving. Okay. So when we measure temperature, when we put a thermometer in a beaker of water and we measure what the temperature of that beaker of water is, we're basically taking a measurement of how fast the molecules in that water are moving. If we put that beaker on a hot plate and we heat up that water and we see the temperature rise, the temperature is rising because those molecules are moving faster. Okay? So heat is just the amount of energy required to increase molecule speed. So we apply heat to something and we increase the molecule speed. Water has what we call a high specific heat. That means that it takes more energy to raise the temperature of water than it does other liquids. Okay? And that is because in order to raise the temperature of water, I'm going to go back to this picture right here. In order to take this water that's over here in this circle, right? We have all of these hydrogen bonds, and those hydrogen bonds are forming and breaking, right? If I want to make, let's just outline this little bunch here. If I want to make all of these 5 individual water molecules move faster, before I can get them moving faster in this fluid, I have to break every one of those hydrogen bonds. So some of the energy that you apply to a liquid in which there are hydrogen bonds has to be used to break the bonds. Then once you break the bonds, you can get the molecules moving faster. Okay, so hydrogen bonding gives water this high specific heat. It means in order for it to actually heat up, you've really got to break those bonds before you can get the molecules moving. Okay, and spread them out a little bit so that you can speed them up. So, because water has a high specific heat and it takes a lot of energy to raise its average temperature, that gives us some unique properties. One of those is evaporation. As a water molecule transitions from liquid to a gas, it requires a lot of energy. So if you want to switch that property or switch that state from a liquid state to a gaseous state, a lot of energy is going to have to be applied. Okay, so that means that water also has a high heat of vaporization. So a high specific heat means that you have to add a lot of water or add a lot of energy to raise the temperature of water. A high heat of vaporization means it takes a lot of energy to change state from liquid water to gaseous water. Okay? That is also really important for life because, as any of us who has ever sweated knows, we cool as our body sweats, right? Evaporative cooling means that as water evaporates from the surface of your body, it takes away heat energy. So if you're exercising and you're really got your cardio going and got sweat running down your face, each time one of those sweat droplets leaves and becomes gaseous water, it takes some of that heat energy away from your body with it as it makes that state transformation. And that's the reason it helps you to cool down. If you're really, really sweaty after a workout in the middle of the winter and you walk outside into a cold New England winter and you get hit with that cold blast of dry air, your sweat evaporates immediately and you start to shiver, right? You get cold really fast. Even in the summer, if you're really sweating, you step in front of a fan and you evaporate all that water really quick. You can actually get goosebumps and have a quick shiver. And that's because all that heat left your body really quickly as you moved all that water from a liquid to a gas. So that's really important in any animal that maintains a constant body temperature. It's going to use evaporative cooling as a way to get rid of excess heat. We evaporatively cool through our skin. We sweat because we have relatively hairless skin. Something like a dog that's covered in fur can't sweat through its skin because the fur is in the way and there's not enough airflow. So instead, they evaporatively cool across their respiratory surfaces. Your lungs are really wet, you have a lot of fluid in your lungs. And so when a dog is panting, they're actually removing heat from their respiratory surfaces and cooling that way. You can see birds panting as well, and they're doing the same thing. They're doing evaporative cooling. Okay. This is all making sense? You guys are getting fidgety. Is water boring? Is that what it is? Yeah. I should have like a drip, 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 like a little musical background. I think water is super cool. That's true. So the other thing that this does, this fact that it takes a lot of heat to change the temperature of water, it also means that water can give off a lot of heat before it cools. So water becomes this great temperature modulator, okay? Because if you have a big body of water, like a nice big lake or an ocean, right, even a big pond, that body of water is going to be doing a lot of exchange with the atmosphere, right? And so that large body of water can take a lot of heat from the atmosphere before it starts to actually warm up the water's temperature. Because again, that heat's going to go to breaking bonds before it goes to increasing molecular speed. Likewise, it can receive a lot of cold temperature from the atmosphere before the water actually starts to cool or turn to ice. And that's because we use that energy to make hydrogen bonds. Well, we use that energy to slow down the molecules, and then we make the hydrogen bonds that would convert it to solid. Okay. So hydrogen bonds are going to be broken before temperature increases and formed before temperature decreases. So the ocean is actually relatively consistent in its temperature, okay, even through most seasons, because it's a very large body of water. There are warm spots in the ocean, there are cool spots in the ocean that have to do with how the water moves globally and currents, but relatively speaking, it stays pretty consistent. Okay, so do large bodies of water, like some of the deeper Great Lakes and big deep bodies of water. They can really modulate that temperature. And that can actually affect the temperature on land. So if you think about like Minneapolis, Minnesota, and Seattle, Washington, if you look at a map, they're on the same longitude, right? But Minneapolis is notorious for being unbelievably cold, right? And Seattle is pretty moderate. And a lot of the moderate temperature that you find somewhere coastal like Seattle is actually from the ocean helping to moderate that temperature. You couldn't achieve those same colds in Seattle because the ocean is helping to moderate. All right. So let's talk about water as a solution. So before we can do that, we need to define what a solution is. A solution is just a uniform liquid mixture of two or more substances. So it could be water and we dissolve some salt in it or some sugar or something. It could be water that is uniformly mixed with something like carbon dioxide gas or methane gas, right? You can mix that water with something in a uniform mixture. I guess methane's a bad example because it would not be uniform. So a solution also dissolves another substance. So it's going to completely surround that other substance and disperse it. So remember our image that we have here of salt, right? You drop this crystal of salt into a beaker of water, the water molecules are going to come and start to surround the salt ions. And our little partial positive charges on our H ions and our little partial negative charges on our oxygens are going to match up with ions in that salt and carry them away, right? Chlorine's getting pulled over here, sodium's getting pulled down here, sodium's going up here, chlorine's going over here, right? And so because of that, those ions are going to get completely distributed throughout the water. And now we just have salt water. We no longer can see or separate or recognize the salt as being independent from the liquid water molecules that were originally there. The only way we get back to that solid salt is if we evaporate off all the water, right? Oops. There, went too far. Way too far. So when we talk about solutions, we talk about the thing that does the dissolving agent, and then we talk about the thing that is dissolved. And so the solvent is the dissolving agent. In my picture that I have here, we have a cup of coffee, right? That coffee in this example is the solvent. It's going to do the dissolving. The sugar that I'm about to pour into the coffee is the solute, the thing that is dissolved. Now, if I just took that sugar and I poured it into some hot coffee and I walked away, eventually the sugar would mostly get dissolved because the coffee is warm enough. It would help to spread those sugar grains around. If I want that to happen quickly, I just give it a couple stirs, right? And by doing that, I add physical energy to those molecules, move them around, and I facilitate the interspersion of my little sugar molecules with my water molecules. Okay? So we say that water is a universal solvent because water readily dissolves anything that's polar. Okay? And that makes what we call aqueous solutions. I'm going to have this underlined because it's not a word I'm going to test you on, but I will warn you that I use the term aqueous solutions all the time. Like when I mean water-based, aqueous will come out of my mouth. So anytime you hear me say that something is an aqueous solution or in an aqueous environment, I'm talking about a water-based environment. Okay? So our cells are mostly an aqueous environment, this water-based solution that all the stuff of the cell is found in. Okay? And then I can't help myself. I love geeky little comics. And so I just think this is funny. The grizzly bear is on shore and the polar bear is in the ocean. Help, help, I'm dissolving. The grizzly says bears are insoluble. It's easy for you to say you're not polar. Right. I need like somebody to do the thumb chunk. All right. So then we'll move on to our last property of water, which has to do with the fact that water molecules themselves readily dissociate into component ions and then reassociate back to water. Okay? So in any given container of water, I've got my water bottle on the table in front of me. I could put water in a beaker in the lab. I can't see it with my naked eyes, but in that glass of water, I have mostly a bunch of little water molecules. That has to do with the bubbling in the glass, has to actually do, I believe, with the water molecules interacting with the gas in the atmosphere. So also at the surface, carbon dioxide and oxygen are dissolving in and out of the water, and releasing into the surface. So all these little blue B's are the water molecules in my liquid glass of water, right? And at any given moment in time, some of those water molecules are falling apart into their component ions. So if we remember, our water molecule is a hydrogen, a hydrogen bound to an oxygen bound to another hydrogen, right? So that water molecule can disassociate in a chemical reaction to become a hydroxide ion, which is OH minus, and a hydrogen ion, which is H plus. Remember, oxygen is electron greedy. So when this happens, the oxygen keeps that extra electron from the hydrogen and becomes OH minus. So it's oxygen, hydrogen, and an extra electron. That's where the minus comes from. And then the hydrogen ion over here has a positive charge because it lost its electron. Now it's just a naked proton, basically. It's just a positive charge floating around. So this happens in water all the time. So here we've got some OH minuses and some H pluses, some little hydrogen ions. And molecules are in motion, so everything in this liquid is moving around. Andrew? Mm-hmm. And now it's just a naked proton. Yeah. It doesn't, its nucleus is a little weak, right? It's just that one proton. So the oxygen is going to run away with its electron. But now, these guys have charges, right? So as they're moving around in the liquid, this hydrogen and this oxygen, or this, I'm sorry, this hydrogen ion and this hydroxide ion bump into each other and they become water again. And these guys over here are going to eventually bump into each other and they're going to become water. And while that's happening, some of the other waters are falling apart into their ions. Just trust me, it happens. It just happens. It's magic. Yeah. Let's not worry about the reason too much. You are going to make everything hard. No. I love that you're thinking about it at this other level. Yes, question everything. And don't believe me when I say it's magic. It's never magic. It's chemistry and physics and the properties of the molecules themselves. Okay. So they're falling apart and they're coming back together, and they're falling apart and they're coming back together. So what that means is that every glass of water, even pure water, nothing else in it, is partially water molecules with a sprinkling of hydrogen ions and hydroxide ions. Okay. So when you think about that, anything that we call an acid, I'm sure you've all heard this term before, anything that is an acid is something that adds hydrogen ions to a solution. So if I cut open a lemon and I squeeze some lemon juice into my beaker full of water, what's going to happen is that the total quantity of hydrogen ions in that water is going to go up. Because the lemon juice is going to donate hydrogen ions to the solution. So now instead of having this small equal amount of hydrogen and hydroxide ions in the background, now we've got kind of a lot of hydrogen ions and not very many hydroxide ions. So now our solution is more acidic than our pure water because it has an excess of hydrogen ions in it. So an acid has more hydrogen ions than pure water, and it has fewer hydroxide ions than pure water. Okay? The concentration of hydrogen ions is up, the concentration of hydroxide ions is down. Depending on what I squeeze into my solution, what I add, what acid I add, this difference will be greater or lesser, right? Something like lemon juice is not going to have as strong of an impact as if I put in a little bit of battery acid or some stomach acid, something really strong. Okay, that make sense? So, when acids dissolve in water, they release hydrogen ions into the solution. Okay? These are, again, those naked hydrogens, no electrons. It's just the hydrogen, just the proton with its positive charge. And so the reason when we talk about needing to maintain homeostasis in our body, we say it's important that we maintain our pH homeostasis. That's that balance of hydrogen ions to hydroxide ions. If you have a bunch of extra hydrogen ions in your solution, all of those little charges want to attach to things, right? Anything that is a full negative charge or a partial negative charge, this hydrogen ion is like, hey, let's get stable, right? It wants to find something else to attach to. And if it attaches to your biological molecules, like your enzymes and your proteins, it can actually change them. So adding acids to a solution can change the other molecules in the solution because those hydrogen ions are going to be reactive. The flip side of that is something that is a base. If something is a base, it accepts hydrogen ions. That means it can pull those hydrogen ions out of solution. So if you have something with an abundance of hydrogen ions in it, and you add a little bit of a base, it'll pick up those excess hydrogen ions. Do you guys have this slide? So bases accept hydrogen ions and remove them from solution. The consequence is that a base has less concentration of hydrogen ions than pure water and a greater concentration of hydroxide ions than pure water. It's not because the base is dumping hydroxide ions. It's because the base is gobbling up hydrogen ions. Okay? So when we're talking about acids and bases and we're talking about pH, we're talking about the hydrogen ion concentration, really. Either we're increasing the hydrogen ion concentration or we're decreasing the hydrogen ion concentration. So here we have a bottle of bleach, right? We pour a little bit of bleach into our pure water in our beaker. And what happens is that that bleach is going to interact with the water molecules and it is going to take out the excess hydrogen ions. And it does this in a two-part step. So here, instead of bleach, I have sodium hydroxide. Na is sodium. OH is hydroxide. This is that ion. Can be that ion, hydroxide ion. Sodium hydroxide, when you pour it into water, falls apart into a positive sodium ion and a negative hydroxide ion. Well, all those extra hydroxide ions hook up with the hydrogen ions in the solution and make water. So the hydroxide ions are pulling extra hydrogen ions out of the water, out of the solution, making water, and you end up with very few hydrogen ions left. Does that make sense? Ish? You're willing to think about it? All right. Let's look at the overall summary and we'll come back to this next week. Okay. So we use the pH scale to determine or to measure or to communicate how acidic or basic a solution is. And pH means potential of hydrogen. So again, we're focusing on the hydrogen ions. Do we have more hydrogen ions in pure water or fewer hydrogen ions than pure water? Okay. This is a logarithmic scale. So for those of you that are really comfortable with math, pH equals the negative log of the concentration of hydrogen ions. Okay. I'm not going to ask you to worry about that, but for those of you who think that way, that's what it is. The scale itself ranges from 0 to 14. Okay. And 0 is the highest concentration of hydrogen ions, and 14 is the lowest concentration of hydrogen ions. So it goes from one extreme to the other. With pure water, our sort of neutral situation being in the center. So pure water, where the concentration of hydrogen ions equals the concentration of hydroxide ions, is actually at a pH of 7. It's right in the center of the scale. And because the scale is logarithmic, each pH increase is actually a 10 times increase in the concentration of hydrogen ions. So when we go from 7 down to 6, so we go from pure water to about where human urine is, we have increased our hydrogen concentration by 10 times. If we go from 6 to 5, we increase our hydrogen ion concentration another 10 times. The reverse is also true. Well, it's opposite. If you go from 7 to 8, so if you go from pure water to seawater, now we've reduced the hydrogen ion concentration 10 times. We have 10 times fewer hydrogen ions. Okay? So as you head towards 14, you're going to very few hydrogen ions. And as you head towards 1, you're going towards I see. My hand and my butt cannot write at the same time. One or the other. So as you get to go towards 0, you're getting to a very high hydrogen ion concentration. Okay? And right in the middle, equal. The same amount of hydrogen ions to hydroxide ions, just like we started off in our pure glass of water at 7. Okay? So when you hear conversations, which are declining now, oddly, about acid rain, right? That's because sometimes, due to our, well, all the time here in this country, due to our output of industrial waste into the atmosphere, rainwater is not a pH of 7. Rainwater comes down acidic because it's actually hitting metals and particulates in the atmosphere on its way down, and by the time it hits the surface or hits vegetation, it's a bit acidic, and it can actually burn water and deface buildings, burn plants and deface buildings. Okay. Seawater, because of the salts contained in it, is a little bit basic. In the human body, we want to be right between 7.2, 7.4. It's really narrow. Get out to 6 and out to 8 in your blood cells, you're dead. Right? We have a very narrow range for life. Our waste materials, like urine, can be a little more acidic. And there are places in our body where we have a lot of acids, like our stomach is actually a pH of 2, but that's because we're trying to digest things and break them up. We have to neutralize them before they leave that compartment. Okay, we'll review this a little bit on next week, either on Wednesday or at our in-between lecture. Okay, maybe we'll do that at the middle of lab. We'll take a poll and see when you guys want to do the makeup lecture if you want to attend it.